Hi, my name is Wolf, and in this talk I want to give you an overview on some of the work that we did on the dynamics of collective learning. But before we get right into it, let us first address the question why collective learning dynamics are interesting. We live in a multi-agent world. That means that agents need to take into account the agency of other agents. Whether we think of biology with animal swarm and collective behavior, whether we think of industry with autonomous robots, transportation and communication networks, or even when we think of policy with collective action challenges towards sustainable development. However, multi-agent systems are difficult to understand and come with a variety of challenges. For example, the environment becomes non-stationary from the perspective of an individual agent, the joint action space suffers from the curse of dimensionality, the number of hyperparameters that need tuning increases, coordination needs arise, and social dilemmas may emerge. Now, I claim that using a dynamical systems approach to study the dynamics of collective learning is beneficial to help overcoming these challenges. But what exactly do we mean here with collective learning dynamics? Let us use the following working definition. It is the interdisciplinary study of collectives of autonomous agents using dynamical systems theory and involving perspectives from machine learning, statistical physics, economics, and theoretical biology. So given all this interdisciplinarity, bear in mind that there is a lot of diversity. So how to approach this endeavor? We start off with the general principle of reinforcement learning, where agents learn through interacting with an environment. Each agent chooses an action A according to its current behavioral policy profile X. The action then probabilistically changes the current state of the environment according to the transition function T, and as a result, each agent receives a reward signal R and observes the next state of the environment as prime. All these processes occur during one time stop of interaction. Then, the agents use the information collected during interaction to adapt their policies, to improve them in order to gain more reward over time. So, here we have a classic, stochastic, independent, model-free reinforcement learning algorithm, like for example Q-learning. Now, several works have shown that if you separate the timescales of adaptation and interaction in the form of a mathematical limit method, you converge to a set of deterministic equations for the behavioral policy updates of the agents. And this policy update equation can be in fact identical to the well-known replicator dynamics of evolutionary game theory. Thereby, the relationship between the two fields is as follows. One whole population in the evolutionary setting corresponds to one agent in the learning setting. However, this deterministic limit method was only worked out for a much simpler class of reinforcement learning updates, those who did not consider a changing and dynamic environment. We refined this method to work also with environmental aware, so-called temporal difference reinforcement learning algorithms that are capable of acting in a changing environment. So what do we find? As a simple test environment, we use here a game called the two-state matching pennies. You can imagine the situation of penalty kicks here with changing roles each time agent 1 chooses the left side of the goal. So it presents a challenge of coordinating on a mixed policy with symmetric rewards but asymmetric environmental dynamics. Now, how can we analyze these learning equations? Here we see reward trajectories, which are quite common to show the learning progress over time. In fact, this deterministic limit method that we derived is general, so we can apply it to different kinds of temporal difference learning algorithms. On the top, we see here two reward trajectories of Q learning, on the bottom 4-actor critique learning, each for two different values of the learning rate alpha, that sets how much new information is used to update the policies. We can also visualize the dynamics in the policy space, where we plot the probability of choosing action left on the x-axis for agent 1, on the y-axis for agent 2. And here we see clearly the convergence to a single joint policy, but also the occurrences of periodic orbits. Third, we can compute a bifurcation diagram, here along the learning rate alpha and the discount factor gamma, that measures how much the agents care for future rewards. It is even possible to compute the so-called maximum Lyapunov exponent from the analytically derived Jacobian matrices of these dynamics. Maximum Lyapunov exponents above zero are a sign of unpredictable, chaotic behavior. So, in summary, we have shown that reinforcement learning dynamics in the deterministic limit exhibit multiple different dynamical regimes, from the convergence to fixed points, to periodic orbits, to even unpredictable, chaotic learning behavior. However, how to interpret this deterministic limit from the perspective of a learning agent? The common replicator dynamics from evolutionary game theory, they have a clear interpretation. They model the dynamics of an infinite population evolving under the pressures of selection. So, in recent work, I constructed a sample batch algorithm that algorithmically separates the timescales of interaction and adaptation. The algorithm will interact k time steps with the environment and the other agents before it uses the sample average of collected reward and environmental state information to adapt its policy. Here we see on the left for a single agent, on the right for a multi-agent environment, that its trajectories in blue indeed approach the ones of the deterministic limit in red under increasing batch size k. However, also the number of required interaction steps with the environment increases proportionally to the batch size, which makes it a highly data inefficient algorithm. Taken together, this sample batch algorithm is a data inefficient, model-free, independent learner. Now, to compensate for this weakness of data inefficiency, we transform the batch learning algorithm into a data efficient learning algorithm that uses a form of memory replay. So we shift the batch of actual interactions with the environment into the memory of the agent, as if the agent learns a model of the environment. And indeed, for an identical batch size of 5,000, we need much less interaction steps. For the single agent environment, learning algorithm and deterministic equations match sufficiently well. For the multi-agent environment, however, they do not. And the reason is that the algorithm is still an independent learner who is not aware of the other agents. Only a true joint action learner who would approximate the policy of the other agents could regain similarity with the deterministic dynamics. Hence, deterministic reinforcement learning can be approximated by a data-efficient, model-based joint action learner. Taken together, this work provides a cognitive interpretation of common evolutionary dynamics such as the replicator dynamics. Agents learn as if they have a perfect model of the environment and the other agent's current policy. Now, to show you an application of collective learning dynamics, let us turn to the challenge of cooperation. In recent work, we examined a collective action challenge under the risk of environmental collapse. Take, for example, the notion of catastrophic climate change. In a classic social dilemma setting, agents can cooperate, which is individually costly but collectively beneficial. Therefore, they are better off not cooperating, which is called defection regardless of what the other agents do. Yet all agents would be better off if they were cooperating. That's the essence of the dilemma. In this work, we extended this setting by an environmental tipping element. Defection is now not only the socially suboptimal choice, but also comes with a marginal probability of collapse. In the collapsed, degraded state, the agent have to endure a negative collapse impact M, and only cooperation eventually leads back to the more rewarding prosperous state. Here we see the parameter space spanned by the collapse impact M on the y-axis and the discount factor gamma on the x-axis. This discount factor denotes how much the agents care for future rewards. Now, by some game theoretic equilibrium analysis, we analytically compute the critical curves that change the incentive structure of this game. For only mild collapse impacts and insufficient future caring, we regain this famous tragedy of the commons, where the faction dominates. For either more severe collapse impacts and or future caring agents, we enter a coordination regime where both cooperation and the faction are equilibria, and the agents have to coordinate on one of the two. And if we increase the severity of the collapse impact or the future caring of the agents further, we can even enter a comedy of the commons, where cooperation is the only equilibrium left. Now, our environmental aware deterministic learning dynamics perfectly correspond to these game regimes. The tragedy corresponds to an all attracting the faction point in the prosperous state. The coordination regime corresponds to a bistable policy space, and the comedy regime, the learning dynamics are all attracted to the fully cooperative behavior. So to highlight only the main result, we have shown that both by game theoretic equilibriums analysis and through learning dynamics, that caring for the future alone can turn the tragedy of the commons into a comedy where cooperation dominates. Of course, this was by no means the end of collective learning dynamics. Towards a more unified treatment of the dynamics of collective learning, I proposed a roadmap forward, which is, according to the nature of these things, always a work in progress. So I suggest to focus on 3 pillars: enhancing the learning dynamics, compiling relevant environments, and integrating different learning paradigms. To enhance the agent's learning dynamics, I propose to work out stochastic dynamics with finite and selective memory calls, develop learning dynamics under partial observability of the state space, and with policies that use observational history. And third, with various types of joint action space learners. To compile relevant environments, I suggest to develop first a classification scheme of the key behavioral challenges, develop the connection to more realistic, complex environments, but also study the dynamics of random environments, which will lead to then a test suite of learning dynamics for the learning dynamics with proper evaluation and analysis metrics. Finally, to gain an integrative perspective on different learning paradigms, such as individual, social, or belief learning, I suggest to look at both an inter and an intra perspective. In the inter perspective, we are interested in comparing multiple pure paradigms with each other. In the intra perspective, we look at the behavior that emerges when agents employ multiple learning paradigms simultaneously. This brings me to the end, where we can summarize. Collective learning dynamics is the interdisciplinary study of collectives of autonomous agents using dynamical systems theory. We have found limits to their predictability because reinforcement learning dynamics in the deterministic limit exhibit various dynamical regimes, from the convergence of fixed points to periodic orbits to unpredictable chaotic behavior. We have found a cognitive interpretation of these deterministic learning dynamics. Agents learn as if they have a perfect model of the environment and of the other agent's current policy. We applied the learning dynamics to a cooperation challenge under risk of collapse and found that caring for the future alone can turn the tragedy of the commons into a comedy. And last, we looked at possible roads ahead, which should enhance the agent's learning dynamics, compile relevant environments, and integrate different learning paradigms with each other. If you have any questions or comments, please get in touch. I thank all my co-authors, and with that, I thank you very much for your attention.